Hi folks, this is Gordon Parker from Michigan Tech, and in this video we're going to look at how to generate differential equation models for a cart system. And this cart system is going to start relatively small and grow up to be a rather large and moderately complicated thing. Now, if you watched any of these other videos, I've done models with blocks and springs and motors and all sorts of things. And what we're doing in this video is bringing everything together into a more complex system. Now, a good approach for modeling relatively complex systems is to start with something small and then work your way up. And that's exactly what we're going to do here. So by the time you're done, you should be able to generate some differential equations of a reasonably complex system and see how to do that using this incremental approach. So here's our example. It looks harmless enough. We've got a couple carts, and one of them has a swinging rod attached to it. You can notice that I have a bunch of green wheels and a red wheel. Well, the difference between those is that the green wheels are not driven. They're just sort of idler wheels, whereas the red wheel has a DC motor attached to it. Let's put down a coordinate frame like so and label some points. You're going to see me label a lot of points in this video, and I'm going to use letters for the carts and then numbers for different little points that might be of interest to us. So the left cart is A, the right cart is B. There are some variables that describe the motion of these things, and here are some of those numbered points. Those are centers of mass. So the center of mass of cart 1, 2, and the rod. So let's get some assumptions going. We're going to have a bunch of them along the way. And the first one is that the wheels are going to roll and they don't slip. Well, that's a pretty straightforward one. And also the only masses that we're going to worry about are the rotating bits of the motor and also the translating bits of the cart and the rotating rod. Now, the idler wheels, those green ones that I mentioned earlier, are riding on frictionless axles, so there's no drag associated with them. So that way we can just model them as if they were blocks sliding on a frictionless surface. And I covered that in a previous video. Now, we're also going to neglect the motor's inductance term, that pesky LA-DIA dt, and we've looked at that in the motor modeling video. And we're also going to assume that the carts are not pulling any wheelies, so the wheels are always on the horizontal surface. Here's the approach. We're going to start by just modeling or coming up with a differential equation model of cart A and the motor, and then we're going to add in the rod, and then finally we'll attach via the spring that cart B. So here we go. So now I've got a little sketch here of the A cart. There's our coordinate frame and the motion variable, XA. And let's define some mass properties. So we have the mass of the wheel, or MW, but it's really not just the mass of the wheel, the red thing, but it's also all the rotating bits of the motor, the armature in particular. Then we have JW, which is the mass moment of inertia of the rotating bits. And we're going to assume that there's a gearhead on the motor. So that means that JW is the effective mass moment of inertia that has the gear ratio in it, N, or N squared, times JM plus that other J, which is everything on the output side of the gearbox. So it's the inertia of the gearbox on its output side and anything attached to it. So in this case, that would be the red wheel. Then we have MC, which is the mass of the cart, except for the rotating bits of the motor. Now let's do a free body diagram. We actually have a couple of them. We have one for the cart, because that has some mass associated with it, and one for the rotating bits of the motor and wheel, because that has some mass associated with it and the mass moment of inertia. Now, one thing you have to be careful about when you're doing these free body diagrams is that that wheel is not only rotating, but it's also translating. And so I've been very generic here, and I've given variables of motion to things like the translation of the cart as XA, and then the translation of the wheel as XW. And of course, they're very much related, and we'll get to that in just a second. Now notice here I've introduced yet another variable, x1 double dot. So I've started the process of labeling the free body diagrams with the external forces and inertial forces. And this one, of course, is the inertial force. So mc x1 double dot. Now I've labeled that as x1 double dot because technically that should be the acceleration of the center of mass of that cart. And there is the weight of the cart, great, and we have a normal force acting at one of the wheel axles. And instead of a normal force acting at the drive wheel, we actually have two forces acting there. We have one in a horizontal direction and one in the vertical direction. I don't know what they are yet, so I'm just going to call them R1 and R3, where the 1 and the 3 correspond to the directions that they're going in. Now you'll probably notice that the R1 is not in the positive direction as E1, but R3 is in the positive direction as E3. It really doesn't matter. I can put those in any directions I want, as long as when I get to the wheel, I put them in the equal and opposite directions. So the first thing I'll do with the wheel is put that inertial force on it, mw xw double dot, and the inertial moment. And now we have the motor torque, which is N, the gear ratio, multiplied by some efficiency, eta, of the gearbox. And if you need to see more information on that, you could go and look at the motor modeling video. And there's our reaction forces, equal and opposite to those that were applied to the cart. There's the traction force, and the weight of the rotating bits of the motor armature and the wheel. And there's the normal force. The only other thing we have to put on here is the viscous damping associated with the motor. And if, again, I've referenced this a couple times, the motor modeling video, but that will present itself on the rotating bits of the motor as bmn squared theta dot. And that theta is the actual rotation of the wheel, not the armature, right? Because the armature is spinning much faster than the wheel due to the gearbox. So a couple comments. The cart only translates, okay? So what that means is that x1 double dot that I introduced earlier is exactly the same as xa double dot and the same as xw double dot. We also know the kinematic relationship between the translation of the wheel and its rotation. So we can express xw double dot in terms of theta double dot. And now what I'm going to do is just kind of zip forward. There we go. So now what I've done is just recopied exactly what I had on the previous page, but into this new page because I ran out of room. But you'll notice in these free body diagrams, I have a little bit of red splashing around. And the reason for that is I've exploited some of those comments from the previous page. That is that the x1 double dot has now become an xa double dot, and the jw theta double dot has now become jw xa double dot divided by r, and similarly for the viscous damping part or term that's applied to that wheel. Now we can go about the task of summing all the forces in the 1 and 3 directions and all the moments, if we need them. So in the E1 direction for the cart, all we have are the inertial force and an R1. That's it. Not too bad. And in the E3, we pick up a few more terms. We have a normal force, a weight, and an R3. And the rotation we could do if we were interested in the reaction forces like the NC. You know, if you wanted to find out exactly when that wheel might come off the ground, then you could work that side of the problem. But we're assuming that the wheels stay in touch with the ground, so we're not going to worry about it. And then we just move on to the wheel. So in the X, or I should say in the 1 direction, we have, if you stare at that free body diagram with all the stuff on it, we have an R1, an FT, and the inertial force in the A direction. And in the vertical direction, we have all sorts of things, an R3, a normal force, a weight, and I guess that's about it. And here we're going to look at the rotation equation too. So we have to add all those up, and we have quite a few terms there, but it's not too bad. You know, there's 4 terms. And I'm going to label these equations 1 for the cart and 2 for the wheel, and give them some additional notation with the A, B's, and C's. Ooh, we can't forget our motor equation. Now you could go back and look at some of those old videos, but the motor equation for a DC motor always looks just like this, where E is the back EMF and I is the armature current, V is the voltage applied to the motor, and we're going to throw away that LA DI dt term. But we also have to keep track of the two algebraic motor equations, that the back EMF is equal to KE, the back EMF constant, times theta m dot, and tau m is equal to KTIA. Now keep in mind that theta m is the theta of the motor behind the gearbox, so it's how fast the armature is spinning. Now if we chuck that LA term, we can rearrange this a little bit, where I've now introduced the gear ratio, and that's why you can see the term KEN theta dot. So the theta m dot has become n times theta dot. And we can write that a little bit differently like this, where we replace the theta dot with XA dot over R due to our kinematics that we had on the previous page. And that's it. So that's IA, and it can be used in the tau m equation, which goes all the way back to the theta equation of the wheel. So here are the 5 equations that we're going to fiddle around with and eventually generate a differential equation model of this cart motor system. So what we want to do is have a differential equation in XA, and that's all we want to end up with. And I'm just rewriting these equations from the previous page. There's nothing new here. Just needed a little extra room. And now we're going to combine things up a little bit. So if we combine 1A and 2A, we get this equation. We can essentially resolve out the R1. Think of it as solving 1A for R1 and sticking it into the 2A equation, or the other way around. And now we can combine this, or combine 2C, 3, and 4, and get this equation. Here I've done a couple things. I've resolved away the FT in equation 2C, basically combined it into this equation. And then also did that little substitution where the IA in 4 goes into equation 3 and then into equation 2C. And voila, we have that thing. Now I can jiggle this around a little bit, kind of group terms, and we get this beautiful differential equation for the cart and motor. So here's our equation again from the previous page because I ran out of room. And now let's just look at a couple comments. Here's our effective inertia, JW, for the wheel that, as I mentioned before, has in it the motor inertia, Jm, multiplied by n squared due to the gearbox, plus capital J. And that J is the inertia of the gearbox on its output side. And here, this is interesting. MW plus MC is the total mass of the cart. And remember, MW is the mass of the rotating bits of the motor, the armature, anything inside the gearbox that's rotating, and the wheel. And MC was the mass of the cart without all that stuff. So it makes sense that the total mass of the cart would be the sum of those two, and that it would be sitting right there in front of XA double dot. Now what's curious is that we can write this differential equation in what I would call the speed form. So XA double dot becomes VA dot, the time rate of change of the velocity of the cart. And the capital V is still the voltage of the motor. Now M, capital C, capital B are these terms. You can think of them as lumped terms. If we know all those parameters, we can calculate these quantities, get numeric values, and stuff them into the equation there by comment 3. What's curious here is that there's really only 2 independent lumped parameters, because I can take this equation and, for instance, divide through by m and get this. So now the quantity C over m is just some numeric value, and B over m is some numeric value. So we have all these parameters, and yet it just boils down to 2 constants. We could also write the equation in this form, which is pretty interesting, where the capital T and the K have a little bit different definition. It's just a different way to divide things through. What's interesting is that when you put this into transfer function form, we get this first order transfer function, a very classic one where you have the DC gain as K and the time constant as capital T. It's crazy. So you have this relatively complicated system, a motor and a cart, and we could model the whole thing with just a first order differential equation, a first order transfer function. And what's even crazier is that if you didn't have all those lumped parameters, the JW and RA, the armature resistance of the motor and the gearbox efficiency eta, you could get them experimentally. So for instance, if you had this motor cart system sitting in front of you, you could give the voltage a unit step input and look at the response. And you might see a classic first order response in velocity like so, and you could pull out the time constant as being about 2/3 or 63% of when it gets to its final value. Okay, so now we're going to add the rod. So there's the rod. Free body diagram is over on the right. And these are all just the assumptions that we had a minute ago. So I'm just going to fast forward to these. No changes here. And everything I do for this cart with the rod and the new stuff associated with the rod is going to be in brown. So here is the assumptions for the rod. We're going to say that its mass is not negligible, and that the rod pin is, however, frictionless. So a couple comments. The drive wheel free body diagram and equations that we did just a few minutes ago are unchanged. So we're going to be able to exploit all of that information real easily. So here's our free body diagram again for the cart, and now we just tack on the rod. Here's a free body diagram of it. There's our coordinate frame. And here's what we have to do for the rod. It introduces a new reaction force onto the cart, the brown one, F1 and F3. And I have it equal and opposite on the rod. Then we have to define a positive sense of rotation for the rod. I'm going to call that phi. And that allows us to put the inertial moment onto the rod's free body diagram. It also has a weight. And the most complicated part of the rod is the acceleration of its center of mass. And I'm going to call that A3. We're going to have to come up with that through some kinematics analysis. And what we'll do is call that acceleration vector A3 as having two components, A31 and A33. So the second number in the subscript is indicating what axis that acceleration is in. Now, one thing to keep in mind is that if we go back to Newton's second law, we know that the sum of the forces acting on the rod is equal to ma. We can rewrite that just by moving the ma to the other side of the equation, and so we have the sum of the forces is equal to negative ma. And that's why I have the negative mr A3 when you apply that concept to the rod. Well, so now let's just sum up our forces and moments on these different bodies. So here's our cart. The only thing that changed from the previous analysis was we now have an F1 in it. And I just snuck in a length of the rod because we are going to need that in just a second. So here's the wheel equations. The E1 is the same. The theta for the wheel is the same. No changes there. So I didn't even rewrite the free body diagram. It was all just unchanged. And here's the motor equation. Again, no changes there. Now let's do the rod. So we have the one direction, the E1 direction. We have a couple things. We have this mr A31. I don't know what A31 is yet, and we'll figure that out in just a jiffy. And there's our E3. That should be an E3, not an E2. But anyway, there is a negative F3. We have this acceleration term, the inertial force, and the weight of the rod. And then finally, the rotational equation of the rod. Now, to get that, you have to do a little bit of how should I say, R cross F sort of thing with the F1 and F3 force. So for instance, if you look at the F1 force, you have an R going from the center of mass, an R vector, I should say, from the center of mass, the point 3, up to F1. And you have to cross that R with the F1 and figure out what that moment is. Another way to think of it is you can just take the F1 and then take the moment arm associated with that vector, which would just be the LC cosine phi. You have to go through a similar exercise for the F3 force. And we'll label these equations 5, A, B, and C, and now move on to the kinematics and get that crazy A31 and A33 term. To do that, I'm going to draw this free body draw this diagram again, and now I'm going to create an absolute position vector to the center of mass of the rod, and I'm going to call that P3. Now I can form P3 with some other vectors. So for instance, the vector from the origin of our coordinate frame to A, and then the vector from A to the pin, and from the pin down to the center of mass of the rod. And I'm going to call that pinpoint 4 because I hadn't named anything for the pinpoint yet, so I might as well call it 4. And there's our direction of rotation of the rod. So here's what we have from our kinematics. We know that P3, the absolute position vector, or the center of mass of the rod, is just PA plus P4 relative to A plus P3 relative to 4. So we've taken a rather complicated task, finding the absolute position vector of P3, and broken it down into a few simpler things. And really what we're trying to do is to get that acceleration, P3 double dot, however you want to look at it, written in terms of the variables that describe the motion of this system. And those variables are XA and phi. And that's what we're going to do. So first off, PA is just XA in the one direction. P4A is just some constant, the distance from that edge of the cart to the pin, so we'll call that D. And then we have P34. So you have to take that vector and decompose it into its components in the 1 and the 3 direction. So we have a little bit in the x direction, the LC sine phi, and a little bit in the positive E3 direction, LC cosine phi. And that's it. And now we just differentiate that twice to get our acceleration. So there's the first derivative, and here's the second derivative. And we've got it. And that's our A31 and A33. So let's put down these equations again. Let me jump and fast forward a little bit. There we go. So that's nothing new. It's exactly what we had on the previous page. And now we can put in our A3. This is what we had on the very previous page, I guess. And now that I've summarized all these equations, we're going to start combining them up. So the first thing we're going to do is to combine 1A, 2A, 5A, 2C, and 4 and get this thing. Now, that's pretty difficult to do in a little, presentation like this, but if you go back to that previous slide where I had the summary of equations, you could go through the arithmetic and convince yourself that you really do get this big, crazy equation. Now we can also combine up all the rod equations, and we get this for the rotation of the rod. And so finally we end up with two rather interesting differential equations to model the cart with the motor and the rod. A couple comments about these equations. Well, things got a whole lot more complicated. You'll notice in that first equation, it isn't all just XA. There's some phi double dots and phi dots running around. And same thing in the second box equation, we have a combination of phi double dots and XA double dots. It's also a nonlinear system. If you have a look at the video on nonlinear systems, you'll be able to just look at these and identify that that's true. You can see things like a sine phi and a phi dot squared and a cosine phi running around in different places in these equations. And so therefore, it's definitely nonlinear. Instead of just 2 independent parameters like we had in the cart motor model, we now have 5 if you count them all up. So it's a much more complicated problem in terms of trying to identify these parameters experimentally. Now, if the rod angle is relatively small, so phi is much, much less than 1, and it is not rotating too fast, so phi dot is much, much less than 1, then we can linearize this model quite nicely, and we get this. So the phi dot squared term became 0, cosine phi is about 1, and sine phi is about phi, and so we get 2 beautiful linear differential equations. They're still more complicated than we had in the past, but they're not too bad. And now we're going to add the second cart. So here it is. There's the spring. I kind of shortened the rod because I was running out of room. And we are going to say that spring is a spring constant of K. The beautiful thing here is that all the equations that we used in the past, we can reuse those. But first we have to deal with a couple assumptions. And one of them is that the cart 2 is a little bit squeakier than cart A. Or I should say cart B is a little bit squeakier than cart A, and that is that there's some viscous damping associated with the wheels. And so with that in mind, let's make our free body diagrams. There is the cart A, really didn't change much at all, except we are going to have to add in a spring force onto that cart A, but we'll get to that in just a second. Here's cart B. There's our inertial force, the MBXB double dot. There's the weight, and there's a couple normal forces. And finally, here's our spring force. So it's acting equal and opposite on those 2 carts. There's a couple ways that you could get that force. You could postulate that the 2 carts have some positive motion. Maybe the B cart has some large positive motion, and the A cart has some small positive motion. You could do it that way. And then you could ask yourself, what does the B cart feel in terms of a force in that positive scenario? And what it would feel is K times the quantity XB minus XA in the direction shown, sort of in that negative E1 hat direction. And once you get that, then you can do the equal and opposite on cart A. Now we have this one other little force, and this CXB dot is due to the viscous friction in those axles. Now you can go through and convince yourself that it looks like this linear term by looking at the kinematics of R theta of one of those wheels is equal to XB, the translation of the cart. So a couple comments. We're only going to have to consider the E1 motion because we're not interested in finding normal forces to determine when that B cart is going to tip and things like that. And we can really just take the model that we had in the previous slide and just augment it a little bit with the purple forces. You know, all the purple forces are associated with cart B, and you can see that there's really only one extra force acting on cart A due to that spring. And then we have the cart B translation equations. So here we go. And we could do this for the nonlinear model, but I'm just going to do it for the linear model. So here we go. We have that for cart A, and there's our purple force due to the spring and cart B. And here's our rotation equation for the rod. It didn't change at all. And here's our translation equation for the cart B. And look at that beautiful linear system. Now, when you look at the purple equation, you go, well, that looks, you know, it's mostly B stuff, but there's that wee little XA term in there. And what's happening, one way to think of it, is that when you apply a voltage to the motor over in the top equation, it gets that first equation going, the XA, and the phi double dot follows closely behind. The rod starts swinging, and of course, when cart A starts to move, that excites that third purple equation, and so cart B starts to move. course, these things happen pretty much instantaneously, but that is the chain of how the input to the system, the voltage, excites the whole crazy system. So here's our linear model. Let me fast forward to that. There, I've just rewritten it. And now what we're going to do is write this in matrix form. Now, I'm going to keep the second order flavor to this thing. So we're not actually going to write it in state variable form. I guess I mentioned that earlier. We're going to leave it in matrix form, second order form. And the first thing I have to do is get this equation. That is, I look at these three equations up top and I ask myself, how many second order terms do I have? And I have an xa double dot, an xb double dot, and a phi double dot. So I first write out that vector. And then I ask myself, what are the terms in those equations that have to multiply by that vector, that three-dimensional vector, so that I get all of the acceleration terms? And there it is. And everything else in these equations, you can just lump into some additional big three-dimensional vector. Now, one thing I want to point out is that the purple equation, my third equation, is actually the second one when I went into matrix form. That's fine. You can put them in any order you want. And here's the right-hand side, the thing that excites that whole system. And one comment is that that matrix, that 3x3 matrix, we call a mass matrix, even though its units are, all sorts of funny things perhaps, but it's symmetric and it's invertible. And that will always be the case. So if you need to do a sanity check on your dynamic system model, this is one way to do it. Put it into second order form, take a look at that mass matrix and make sure that it's symmetric and invertible. Now this form is really useful for getting into state variable form, because to get to state variable form, you're going to have to solve for those xa double dots, xb double dots, and phi double dots. And to do that, you can just invert that mass matrix, multiply it through, and voila, you have those expressions. And that's it. So this was kind of a long video, a lot of stuff going on, but basically we just went after modeling a relatively complex system, bringing together a lot of things from other videos in terms of gears and motors and blocks and all that kind of stuff. But we did it in an incremental fashion. I highly recommend using that approach for modeling complex systems. So I hope this helps. Thanks for watching. Bye-bye.